Now we're going to get to the code. So on the website, there's an 831 piece of code. I'm going to open up here. So this has a whole bunch of stuff in it. Well, actually, it's only about 6 lines, 6 to 8 lines here. In fact, this is it. I'm going to run it, and then we're going to see what in the world happened, depending on how you wrote it. I put a t, then a y, then a k, then a t external. So I just have to match that, and then it should be fine. Lovely. So what we just did there was simulate the temperature of an object, and we know what the prediction should look like. It should look like an exponential decay down to the external temperature. And if we take a look up top here, we said, hey, the external temperature will be 20 degrees. There'll be some constant for the decay, and the initial condition will be 100. So a lot of those first lines are just saying, hey, what are my constants in this particular problem? I'm just going to go back to the notes for a second and sort of walk through what each of these lines does for interest's sake. So just to explain this a bit better, this is just defining a constant. This is just defining a constant. Nothing new there. This is important. This is more fundamental here. This is the real function of t and y only. And that's what we actually need for the solver. So our function, temperature differential equation, had a t external and a k. Those got defined earlier. Get them right here. There's k, there's t external. What we're doing here is saying that was great. The temperature had more information it needed, but I need a little shortcut function that I'm going to call capital DE that is just t, just y. That's all it needs. Everything else it needed I already defined beforehand. This does no calculation. No calculation. What this does is it builds a little hierarchy. It says I've got a function called DE here that takes in t and y. And when someone hands me a t and y, just like the cosine function doesn't do anything until you say take cos of this number, the DE function just sits there. But if you ever handed it some t's and y's, it would hand it off to the temperature differential equation function, which took t, y, k, and t external in, and did some calculations, and came back with dy dt. That would get handed back to the differential equation, which would hand back dy dt as well to the main program. So we are going to be building a relatively complicated stack of functions that are calling each other. You've actually been doing this all along, but they've mostly been MATLAB functions, built-in ones. Now we're building our own. So there's going to be a function that I can call with t and y values. It'll pass the t and y into here. It'll use the hardwired k and external temperature to calculate the slope. And that'll get passed to here, but it just passes it back to the next layer above that. But nothing happens until we have some t's and y's. Then we get to the fun part. This constant, this constants. So far there's only been one line of actually interesting code. This, as soon as you see this ODE 45, this is running the simulation. That's the line that does the work. Nothing actually happens, or no calculations are performed until you hit that line. But this is the setup of, hey, I know my initial temperature is 100 degrees. I'm going to simulate for a time span of 30 minutes, I think were the units I picked here. And I have the rule, which is my differential equation. That's the rule for how y changes. As soon as I have all that, again, in principle, I can go, hey, I can predict the temperature or simulate the cooling off of this object for the 30 minutes that you told me to simulate it for. And it can go ahead and do that. It has all the information it needs. And at the end, we're going to plot it. Most of the code here is just constants, setting up values that will be used in the simulation. There's one little technical thing to make a differential equation that MATLAB solver would like. And then we actually run the solver with the 3 inputs that we need: time span, starting point, and the rules of the game, the differential equation.
T and y are never defined specifically anywhere.
That is right. And this is the most deeply uncomfortable thing. T and y are never defined. And think about y for a second. T and y, what I know about t and y is nothing. I know t0 and I know y0, right? The simulator is going to take care of time changing and then the y changing as a result of that. I don't know that yet. I'm trusting someone else is going to do that for me. So at the beginning, exactly, these are functions that could take any t and y in potentially, but I'm not giving it to them. The solver is going to do that for us. That's what the ODE45 function does, exactly. And I think we're actually at the stage where it makes sense to talk about what in the heck just happened with that. Actually, let's decipher the output first, and then see what we get from that. So the simulation results. This is the simulation line, ty. The thing we get back, these are concrete t's and y's. These finally, and it's horrible notation. The fact that t and y here are inputs to something else, but they're never defined, whereas down here, the exact same looking names, t and y, are now all of a sudden vectors. Well, that's the way it works sometimes. The fact that we said ODE45 on the right-hand side is going to equal t and y, that means we calculated something and we get t and y back. So I'm going to take a look at t. It's actually right here in our workspace. It's a vector of 61 numbers. What do you want to bet the first number in that vector is? Excellent. What do you think the last number is? 30. Right. Let's take a look. T, last number 30. First number 0. Fantastic. All the numbers else in between. So what this is on the graph is a sequence, because we're simulating here, and I didn't mean to do that. What we're doing because we're simulating here is getting a bunch of time values that are numerically generated. So we get a sequence of time values, not all of them, because it's a computer, it only can give us so many finite numbers back. But it gave us 61 values back, the first one at 0, last one at 30, and 59 more in between. And perhaps unsurprisingly, there's y's that go with that. Now, we don't know all the y's, but I know what the first y should be. It should be what? 100. OK. Why not? Equals 100. That's setting. Why not? Y0 is 100. And so if we scroll up to the top here, we get 100 as our first value, and then it's 95, and so on. These go as a partnership. So the important thing to recognize is that there's exactly the same number of y's as there are x's, or sorry, t's. And what we could do to make that more obvious is put them side by side. ty as two columns. There we go. What we're getting is, at this time value, this is my temperature. At this next time value, there's my temperature. So we've simulated the cooling process by saying, at these times, here are the temperatures we end up at. And if we look at our graph, that's the behavior we see. We see at certain times we have certain temperatures, and we've simulated that cooling process by this ODE45 command. So t is going to be a vector of values. T is a vector of values. That's a column vector. Y is a column vector of values as well. That's the same size. So same size, because it wouldn't make any sense otherwise. I'm trying to predict things. First value is 0. Last value is 30. More generally, this would be t naught, and t final is what we usually call them. And this was 100 in here. More generally, that would be your y naught value. So start my simulation at time 0 with temperature 100, and then see what happens. Stop, because we can't run forever. Stop at 30 minutes, and then tell me what the simulation was over that time span. So that's the fundamental idea. Again, questions, comments now about the structure of the output.
What determines the number of like ty?
Right. Why do we have 61 data points and not 5,000 data points coming back out? Well, it probably won't shock you now, but what was the last technique that we covered in integration? Let's take a look at the help menu here for a second. If we look up quad in here and numerically evaluate integral adaptive. The techniques we saw last time for numerical integration said, OK, I have an interval I need to integrate over, but I want to cut into subdivisions only as small as I need to get an accurate answer. So it adapted the step sizes. ODE45 is an adaptive differential equation solver, so it picks the number of sizes based on an error target. And we'll talk about that before the end of the week, how we can dial up the error, dial down the error, but that'll cause more cycles to be required, more steps to be required. So we're using an adaptive solver for this, which is why we can't predict in advance how many values we're going to get back. So before I talk about the process, what I want you to capture right at this moment, input. Everything up to here is setting things up. Nothing happens there. This line is the line that does all the work, and then we just plot our output. So if you can get that black box idea of read this as ODE45, oh, I'm simulating this differential equation rule for this time span starting here, and I get back the interpretation of the results is going to be what messes sort of half the class up when you go to work with this. I get back a bunch of time values starting at when I said to start and ending when I said to end, the ones in between somewhere adaptively picked, and the matching predictive y values, the simulated y values. Oh, that should match those time values. That's the simulation. That's exactly what a simulation is. Over time, what's my thing doing? Here it's over time, what's my temperature going to be? If you can get that, you've got it all. Just get an idea of what the matrices vectors look like, and we're good to go.